Last but not least, Eduardo Pereira. Eduardo holds a PhD degree in astrophysics from the Brazilian National Institute for Space Research, INPE. He has completed postdoctoral research in cosmology in INPE, computational astronomy, University of São Paulo, USP, and artificial intelligence, Unicamp. He works as a technology specialist at SENAI in San Jose dos Campos, focusing on topics such as artificial intelligence, embedded systems, computer vision, modeling, and simulation of physical processes. Eduardo, thanks a lot for your last-minute availability. Was much appreciated. I know that there was a delay, but you promptly reacted. Appreciated very much, and I leave the floor to you.
So, thank you very much, Danilo. So, for me, it's a great opportunity to stay here today. I would like to thank you very much, Danilo, for this opportunity and share it's my first time in this forum for tiny machine learning. And I recently started to work with tiny machine learning and on-device learning. But in my case, I'm interested in using the available hardware in the marketing. So we have a lot of hardware available today. And the question is if it's possible to make some robust or to have some robust implementation of a machine learning algorithm that run online learning algorithm that run in this kind of device. So we have a very limited research device with a low memory and low computation process. And the key point is it's possible to have a robust machine learning algorithm for online learning in this kind of device. So the advantage to use this family of devices, the accessibility. For example, in the industry, if you have to implement this low-cost sensor to monitoring a lot of equipment for a middle industry, so this is a big advantage to have the possibility to run machine learning algorithms in this kind of equipment, and also to run in particular for this three family of sensors that is very common sensor and relatively easy to access to have this sensor nowadays, this microcontroller nowadays. We have a big advantage to run in this kind of hardware. So the question, what kind of machine learning algorithm is possible to run? We know that it's possible to run some neural networks in this case, or in this kind of microcontroller. But training in real time, we train a neural network. We know that is a prohibitive to train a large or a more complex neural network in this kind of microcontroller. However, we have alternatives algorithms, and we explore one another alternative theory in order to have online learning for this kind of the dispositive. The key point when you work with neural network, neural network has the power of generalization. So you can train different functions, and no matter what is the function, we can learn the pattern from the data and encode this pattern in a neural network. But when you are trying to develop some algorithm for a specific case, not necessarily we have to work with a generalized model, but we can start to work with some specific theory that can solve our problems. In particular, for anomaly detection, the external theory can be a good theory used to implement a machine learning algorithm in this kind of devices. The big point for the anomaly detection is that is important, for example, in the environmental location parameter based on sensor reading. So we are monitoring some equipment, and it's important to evaluate if the equipment is in a normal state or have some anomaly or some abnormal pattern in your behavior. For example, to turn off some equipment if the vibration started to higher than the normal pattern. So when you talk about anomaly, we are talking that our input data have a normal behavior or a normal pattern, and for some reason we started to have some deviation or a big deviation from this normal pattern. So this is when you talk about anomaly in general, we just talk about this, the deviation from the normal pattern of a data. And anomaly, we can classify typically the anomaly in 3 classes. So we have a point anomaly. So here we can see we have a normal pattern for our data or a time series. We have a normal pattern for this time series. And sometimes we have a big deviation from this normal pattern. So this deviation can be classified as an anomaly. We also have a contextual anomaly. So our data has one kind of behavior, and sometimes we have observed some changes, but it's not in the behavior, but we also has some anomaly. So this anomaly can be classified as a contextual because depends of the kind of behavior of the data in that given moment. And also have a collective anomaly. So if you have a sequence of anomalies in our time series, or consecutive anomalies in our time series, we can classify this anomaly as a collective anomalies. So in this work, we try to evaluate and classify this anomaly from the data. In the literature, the common way to identify and classify anomalies using conventional techniques like spectral analysis, autoregressive models, and also using neural network or deep learning neural network like a recurrent neural network or generative models. We also have a composite model that combine conventional techniques and deep learning neural networks. So in this case, we need a lot of data and also a variation, a lot of data, and also a big computational resource in order to have to train our system and in order to have a good model to classify and identify anomaly in this case. Also, for anomaly detection on device using this kind of microcontroller as Raspberry Pi Pico, another approach is using a random forest. So the use of a random forest for this kind of device, like a Raspberry Pi or Arduino or microcontrollers, the problem is that we are limited of the number of trees that we can be used in our random forest. Sometimes if you use a lot of trees in our model, we have the memory limitation. But if you use few trees in our random forest, we have the problem of bias in our classification model. So we're using low trees in our forest model, we have a very biased result. But our device limited the use of trees in the system for online learning in this case. Alternative to evaluate particularly the anomaly is the extreme value theory. So in general, when we observe a data, we have a distribution from the data. So we started to collect the data, to analyze a lot of data in order to reconstruct the distribution function for a given data. But for extreme value, we started to look not for all the data, but only for the extremes and the tail of our distribution. So we start to focus on the evaluate only the extremes points from our data. So the anomaly, because we are interested in anomaly, if something or some data is greater than or is out of this tail, this data can be classified as an anomaly. So in this case, if you have a good fit or a good distribution only for the extremes, we are able to classify a new point as a possible anomaly or not. For example, in this case, we have for a given time series. So in this time series, we set up a threshold. So the extreme value theory, we needed to limitate our data. So we are interested only in the tail. So we have to start a limitate or put a threshold in order to start to evaluate the extremes. And another point is that we are looking only for the peaks in this case of the time series. So we need to select the peaks above a given threshold. After that, we use these extreme values to learn a Weibull distribution or extreme parameters of a given CDF or a given cumulative distribution function for an extreme distribution function. And now we have a probability distribution function to classify a new input data as extreme or not. And at the end, we have a new threshold. This threshold is for the CDF, for the cumulative distribution function, that we use it to determine if a new point can be classified as an outlier or anomaly or not. For example, in this case, we was using the previous 5 data to fit this extreme distribution function. And the last data used for this point was used as input for the cumulative distribution function. And this function returned a value greater than the value equal 94%. So we have a 94% of probability that this data is extreme compared with the previous extreme. It's like, we are indicating that this extreme is extreme compared with the previous extreme. So this is the key point of extreme value theory to analyze or to identify anomalies in time series. The heart of the general, the extreme value theory is the extreme value distribution function. So we have a generalized extreme distribution function, but because you are interested in the boundary data, we are putting a threshold in the data in order to start to analyze the extreme. This theory, the extreme value theory, indicates that for this particular case, a Weibull distribution function is a good function to evaluate or to try to estimate this CDF, this cumulative distribution function for extreme data in this case. So the CDF for the Weibull distribution function is given by this equation, and we have here 3 parameters. So we need to only learn 3 parameters in order to classify a data as an outlier or not. But because we are working with streaming data, we have a sensor, we are streaming the data. This parameter, color of location parameter, we can set up this parameter is a 0. This parameter is used like a time shift in our analysis. So we can set up our time, we turn on our sensor. So because we are turning on our sensors to start to learn the extreming, this parameter can be set as 0. So we have just 2 parameters that we need to learn from the data in order to classify a point or a data as extreme or not. But because we are working with streaming of data, you need to have some conditions because we to evaluate if a point are or not with a data, to evaluate the streams in the given set of data. So my approach for the streaming data from sensor was use a time window. We set up a window, and we started to collect the data in these windows. I mean, we have a lookup table to to save this data, the data collected from a sensor, and we needed to analyze not only this extreme, but also we need a way to define in a more dynamic these thresholds. So we need to define in a dynamic way the threshold used to start to evaluate extremes in this case. But well, using a time window, you can use the standard deviation of the data inside the window as a possible boundary condition to start to look at extreme values. So the approach I used in this work, in my work, was set up to start to looking for extreme above a given gamma parameter. I mean, I started to looking for extreme above 2, 3, or 5, or greater than sigma. So I use the standard deviation of the data inside of the window to dynamic set up this to get these extremes in this case. The code was implemented using a MicroPython. MicroPython is a lightweight implementation of the Python 3 to run in MCUs or microcontrollers. And also we use the ulab, that is a library, light version of NumPy and SciPy library to run in MicroPython. Here is just an example of the code using ulab to run the functionality of NumPy into microcontroller. So we can run in this common microcontroller available in the market code that's learned in real time and using MicroPython to do the implementation of the algorithm. Basically, what the algorithm doing is, when we start to turn on the sensor, or the algorithm starting the learning mode, and the learning mode, we started to collect the data, evaluating the data inside that given window, and selecting the extremes from that are above some value or some multiple of the standard deviation of the data inside a given window. When you have sufficient data or extreme data, the algorithm started to learn the Weibull parameters, the function, or the extreme distribution function, and the system is out of the learning mode and starting the evaluation mode. So the evaluation mode, all data collected is used as input for a distribution function. And if my CDF return a value with high probability of the given data to be extreme of extreme, the data is considered as an anomaly. And also we have a new lookup table to put this new outliers when you save these outliers and evaluate the time occurrence between these outliers or these anomalies. So if the number of data anomaly detected is greater than a new threshold, we can classify, for example, this data as a collective or a contextual anomaly. So it's depending of the time range occurrence between one to another anomaly. So the system, all the lookup table used a first in, first out scheme. So the first data that enter in the lookup table is the first data to out of the lookup table. So we are dynamically allocating our our data, because we are working with a limited resource, we need a way to evaluating in a more real time this data and the anomaly. Also, at the end, if you have a continue, for example, if you have a collective anomaly, but we have a continual anomaly, I mean, all new data can starting to classify as anomaly. In reality, you have the system in a new regime. This new regime can be classified, indicated that the system has a problem or something very different of the normal is happening with the system. Not that. Instead of using only one point data in the time series to classify if the system has a problem or not, we use a continuous evaluation of the input data in order to define if the system or if the monitoring system has a problem or not. So, because this kind of approach avoid the problem of the false or negative classification for anomaly detection. For example, if you have a motor or equipment connected, eventual anomalies not necessarily indicated that we have to stop the equipment. But if you have an occurrence in the constant occurrence of the anomalies, in this case, yes, we can stop the system. So these are a way to make a more accurate and a better decision about what you have to do with the equipment if we detect anomaly or not. And also, all this kind of decision and all of this evaluation is running in real time in devices like a Raspberry Pi Pico or some ESP32 devices. At the end, we have at least 5 meta parameters. So these parameters, we can evaluate what the best set of parameters for a given case. So we have a parameter for the bounding function, for how much we have to consider the standard deviation, the data above the standard deviation, to start evaluating this data as a possible extreme in order to using this data to learning the extreme distribution function, the threshold parameter for the CDF to effectively evaluate if a new data can be classified as an anomaly or not, the number of points used to train the Weibull function or the CDF function, and so on. Another important point is the rate of sample, the sampling rate of the data from a given sensor, for example. So if you use a very short time range between the sampling, we can get a lot of noise. But if you have a long time, sometimes we lost some important signal. So this is important to have a very good fit for these parameters in order to have a good result in the anomaly detection sensor. I made some experiments changing these parameters. Here is the initial setup experiment. So we have here a Raspberry Pi Pico and an EMU 90 degree of freedom sensor to evaluate the gyroscope and accelerometer. Here I focus on using the gyroscope information to collect the vibration from this system. The Arduino was used to control the cooler, and the coil I used to make some movement, manual movement, in order to introduce or simulate anomaly in this kind of system. So we have a very simple experiment, but we can make some robust tests using this kind of experiment in the algorithm. Here we have the starting the experiment. So we have the starting, put the system in a normal mode. And after some time, the system collects sufficient data to understand what is the extremes from the normal, but these extremes are classified or used to identify what is the normal behavior of the data. At this point, we have a sufficient data, extreme data, to use it in the learning algorithm to learn the distribution function. And after that, we start in the induce or emulate or simulate some anomalies in the system. So we can observe here that now we have the cumulative distribution function trained. So we know the distribution function for this data, and here we can observe that these extreme values was detected as extreme when compared with the previous data. So the key point is that it's possible to have a robust algorithm that run in this kind of device. So it's possible to have online learning and using streaming data from sensor, and to not only to learning the parameter of the normal state of a given system, but also to make some inference and classify the new data as an anomaly or not. Another experiment was made using industrial motors. In this case, we have here Raspberry Pi as a broker. So the data is transmitted from this ESP32 sensor into this Raspberry Pi, and we collected the information of this broker in a computer or in a cloud computer. So we have a completely edge computing system here to evaluating and in a real time a system. So here is the running experiment. I changed the nominal frequency of operate of the motor. So we reduce in a half the frequency of the operation of the motor, and test if it is possible to identify this changing using the present algorithm. So we can observe here that when you reduce the operational illumination, the motor work changed, and we can detect this changing. Now we return the frequency operation to 16 Hertz. So we return to normal operation. This is the nominal operation of the motors, this motor. And returning to this operation, we recover. The system indicate that the system are in normal mode. Reducing again, we can observe that the reduction of the frequency operate was detected as a changing or anomaly in our system. Here is the fit, the data collected in this case. We can observe here the moment that I make a more long experiment, and was able to detect this changing in the regime or in the nominal operation frequency of the motor using the vibration, and also the system learning this normal operation in real time from this device. So the basic idea of, in this case, is that we have a sensor data, like a IMU for vibration, temperature, pressure. The data is pre-processed. For example, in order to reduce noise, we can use it for a simple moving average in the previous data, in the collected data, in order to have a more smoothed data. And this smoothed data can pass it for the tiny anomaly detection algorithm. the algorithm starting the learning mode. So after to learning the parameters of the extreme distribution function of the data, of the current data. So the system learning where is the stream, a normal streaming extreme for a given data, and this data and this processed information is published in a broker using a MQTT protocol, for example. In a complete scenario, we have a group of computing, foggy computing, making the computation inside the sensor, for example, and the information is sent to a broker. And an alternative way, or a complementary way, we can have the information not only if a data collector is an anomaly or not, but also we can pass the learning parameter of the extreme distribution function to a broker, to a edge computing, and this edge computing for example, into the Raspberry Pi, you can use this the combination of the learning function to obtain an ensemble and have an ensemble learning from the data. So instead of to decide if anomaly using only the information from the sensor, we get a collection of the sensor of the same kind, in the same kind of equipment to decide if the system is in anomaly behavior or not. So that is. Thank you again, Daniel.
Thanks a lot, Eduardo, for your great presentation and explanation. I think it was very interesting to know how you applied and implemented extreme value theory for anomaly detection. That was very informative. We're running out of time, actually, my fault, but just a quick question for you. You spoke about edge devices, and initially you were listing a number of boards. The question is, how tiny do you think you can go in your deployment? I mean, how tiny can be the processor that you can use to implement the anomaly detection based on extreme value?
So if I understood the question, the point is how tiny I can put my algorithm in terms of hardware and software. So we can, the big challenge here, if you have a lot of sensors, for example, we have a 6 degree of freedom EMU. You have the limitation of the window, the size window, in order to put this data in the memory of, for example, Raspberry Pi Pico. But I think we can use this kind of sensor, a low limitation, a few kilobytes of memory. We can implement it for analyze 4 or 5 sensors at the same time. So we can put, for example, temperature, pressure, vibration in 3 or 6 axes, for example, X, Z, and Y for vibration accelerometer. So I can think this is the limitation of the usage in this case of this kind of algorithms, of this kind of approach. But if you save the data, put in a more robust computing like Raspberry Pi, that a single computer board or FPGA, we can improve this process or the quantity of data that we can collect and analyze in this case.
Excellent. I think very few kilobytes scalable to more memory allows different type of data.
Yes.
Good. Thanks again, Eduardo. Very much appreciated your contribution. All the TinyML operations are possible thanks to the strategic partners. which are providing the support and commitment to make and to keep successful all the operations, the different events that TinyML Foundation organizes. So thanks to IZIP, Analog Devices, Arduino, ARM, BrainChip, EdgeImpulse, Dreamwave, Technology, Groverty, IBM, ImageBob, Infineon, Innatera, Microsoft, Nota AI, NXP, Pauling Technology, Pixel, Qualcomm, Renesas, Schneider Electric, SensiML, Sony, Silicon Labs, STMicroelectronics, Synaptics, Syntian. Then our executive strategic partners, EdgeImpulse, as I said, Qualcomm, Syntian, the Platinum one, which are Renesas, then Aetrios. Gold strategic partners are Analog Devices, Arduino, ARM AI, Infineon, Innatera, Microsoft, SensiML, STMicroelectronics, Synaptics, and the silver strategic partners, as I said before, IZIP, BrainChip, Dreamwave Technology, Groverty, IBM, ImageMob, Nota AI, NXP, Pauling Technology, Pixel, Schneider Electric, and Silicon Labs. All the rights are reserved to the TinyML Foundation, and thanks again for your time, for your patience, also the extra time.